Hello everyone, welcome to the Luminous Science. Today we are going to discuss about an interesting topic, the Raman Spectra. So now let us see the quantum theory of Raman Spectra. As we know, this Raman Spectra was invented by C.V. Raman, who is one of the most famous and a valuable, precious scientist in the world. And it is proud to say he is an Indian. Now let us see the quantum theory of Raman effect. The occurrence of Raman scattering may be most easily understood in terms of quantum theory of radiation. This treats radiations of frequency, which is represented by mu, as consisting of a stream of particles. So here the particles are referred for photons having energy h nu, that is E is equal to h nu, where nu stands for frequency and h stands for Planck's constant. So in quantum theory of Raman effect, we can see that the electromagnetic radiation, which we usually use in other kind of spectroscopy, here the radiations are actually treated in the form of frequencies. So the radiation which passes from a source to an object or a sample which is to be studied are actually considered as a stream of particles. So the radiations are considered as particles, and those particles are specifically mentioned to be photons. So these photons will have the energy of h nu, that is E is equal to h nu of the photons present in that radiation. So here nu stands for frequency and h stands for Planck's constant. Photons can be imagined to undergo collision with the molecules, and if the collision is perfectly elastic, they will be deflected unchanged. So usually during the source of radiation, when the radiation will be moving in one direction, we can see there will be continuous movement of particles or the photons which is present in that radiation. And due to the movement of photons, there can also be chances of collision taking place between the particles. So those collisions which take place may be of two types. That is, one is elastic and the other one is inelastic. So in case of elastic collision, we can see there will be no exchange of energy seen between the photons or atoms. So in some cases there will also be inelastic collision that actually leads to exchange of energy between the atom. The exchange of atom and no exchange of energy between the atom plays an important role in the type of spectra we get in Raman spectroscopy. So here that is what it is mentioned. So when the photons undergo collision with the molecules, and if the collision is perfectly elastic, they will be deflected unchanged. That is, the exact image or the exact spectra will be reflected upon the screen or in the monitor. So here we can see the scattering of light. So scattering of light, as mentioned earlier, are of two types: elastic collision and inelastic collision. In case of elastic collision, there will be no change in energy, but in case of inelastic collision, we can see exchange of energy. Here let us see the definition of elastic collision. When we pass stream of light on a molecule, it collides, and during this collision there is no change of energy. For example, here we'll consider an atom or a photon. We'll consider a photon A, and here is another molecule, or let us consider this as a sample. So during the course of motion, and if this photon, now let us consider a photon has an energy of h nu. When this photon comes and hits a molecule, if this collision is an elastic collision, then there will be no energy exchange. That is, the energy A will possess h nu, and let us see the energy which is present in B is h dash nu dash. So this will be the energy which is present as it is, and there will be no exchange of energy. But if we see in case of inelastic collision, in inelastic collision, here the energy will be exchanged or energy will be changed. So when A, that is photon, hits a sample or a molecule, there will be obviously exchange of energy or sharing of energy. And thus this exchange of energy and sharing of energy takes place only when there is an inelastic collision. Here the energy will change, that is, it may decrease or increase. So there are two cases: it might increase or it might decrease. On the basis of increase or decrease of energy, so as we know, there might be increase in energy or decrease in energy. So on the basis of this increase or decrease of energy, the Raman scattering is divided into two types, that is Stokes lines and anti-Stokes lines. As mentioned, Stokes lines and anti-Stokes lines. So here nu represents the frequency and R represents the Rayleigh line. So let us see what is Rayleigh line next. So now let us understand what is this Stokes line and anti-Stokes line. Now let us consider the different energy level. Let this be N0, N1, N2. This is with respect to all three different energy level. And here we can see three different types of transition which takes place during the collision, or also we can term this as the transition of electrons or atoms in their energy level may also occur in three different ways. In the first way, when incident radiation hits an electron, the electron from its zero energy level will jump to its highest energy level, and after some time, obviously the electron will lose energy and return to the N1, that is one energy level higher than the initial energy level, and which will emit a radiation that is h nu minus delta E. Why this minus delta E mentioned is the electron is not completely relaying to the n0. N is equal to 0 energy level, but it is resting into N is equal to 1 energy level. And this is one energy level higher or lesser when compared to the initial energy level, and there is loss of energy which is seen. That is why here minus delta E. And such transition where the electrons or atoms from their minimal energy level, that is N is equal to 0, will move to the higher energy level and get back to the energy level greater than that of the initial energy level is called as Stokes line. And similarly, when an electron or atom due to incident of radiation from its minimal or the zero energy level will jump to its higher energy level and return again to the initial energy level, that is 0 only, and also emit radiations which is h nu. Such type of transitions or such type of spectral lines obtained are called as Rayleigh line. And another type of radiation when the electron will transist or transform from its one of the highest energy level. Now let us consider this as 1, 2 and 0. If the electron jumps from n to n is equal to 1 to its highest energy level and will return back to the energy level which is lower than compared to its initial energy level, that is n1. Here it is at n0, and which will emit a radiation or energy which is h nu plus delta E, because it is returning to one energy level lower than its initial energy level, and thus here the energy must be added, so more amount of energy will be released. Such transitions or line spectra that is obtained during this transition is called as anti-Stokes line. Their complete definitions, we'll see it now. So before going to the definition, let us see the order of energy in terms of frequency. So how much energy is needed for such transition when we consider the frequency? And we know the amount of energy which is released during the anti-Stokes line is more, that is plus delta E, but in Stokes line we can see it is minus delta E, and therefore the order of energy in terms of frequencies, anti-Stokes line will have greater energy when compared to Rayleigh line when compared to Stokes line. And similarly, when it comes in terms of wavelength, we know that energy is inversely proportional to wavelength, that is if energy increases, wavelength decreases. If wavelength increases, energy decreases, and thus this order will be reversed. In terms of lambda, the energy will be more for Stokes line when compared to Rayleigh line and when compared to anti-Stokes line. Now let us see what is Rayleigh line mean. When a photon strikes a molecule, the energy is absorbed by the molecule and it gets excited to some higher energy level. In case it returns to its original level, it will emit the same amount of energy as absorbed, and thus we have the scattering known as the Rayleigh line scattering, and the line is known as Rayleigh line scattering. So as seen earlier, if the transition or the movement of electron or atom from its energy level 0 and returning back to its same and original energy level, such types of scattering is called as Rayleigh line scattering, and the line which we obtain from it is called as Rayleigh line. And when it comes to Stokes line, however, in most of the cases the excited molecule will not return to this original level. It may return to a level higher than this original level, that is as seen in this first case. It will not initially get back to it n is equal to 0, but it will go and land in n is equal to 1, and thereby will be then emitting less energy than the absorbed. This is known as Stokes line, which is given by h nu minus delta E. So the amount of energy which is released will be lesser when compared to the Rayleigh line, that is h nu minus delta E. If we see the definition of anti-Stokes line, the excited molecule may return to a level lower than that of this original level. That is, if the excitation is starting from n is equal to 1, but at end of the excitation when degeneration takes place or deprotonation or degradation of a photon from its higher energy level to lower energy takes place, instead of landing into n is equal to 1, it will land at n is equal to 0, and thus more energy is emitted than the absorbed. So the amount of energy absorbed will be lesser when compared to the amount of energy which is given out. So this type of lines are called as anti-Stokes line, which is represented by h nu plus delta E. Now let us see a derivation which is related to pure rotational Raman spectra for diatomic molecule. Here we are considering a diatomic molecule, and we know that the energy of rigid rotator, the energy for rigid rotator will be E is equal to h square by 8 pi square I into j of j plus 1, which is represented in written in terms of joule. And when we have to write this in terms of wavelength, we will just change this j term in terms of centimeter inverse. So the unit representation will be changed, and also there will be a slight change in the equation also, that is E is equal to h by 8 pi square IC. So here we are simply dividing the whole term by HC. When here also HC comes, so H will obviously get cancelled, that is square, and the remaining term will be ER is equal to h by 8 pi square IC into j of j plus 1, which is written or represented in terms of centimeter inverse, which is nothing but wave number. In simpler terms, we can write ER is equal to Bj of j plus 1, which we call equation number 1, and we also know that B is equal to h by 8 pi square IC. So to simplify this equation and also for fast understanding, we consider B. We also know B stands for rotational constant, and thus also we have seen the derivation which is related to rotational constant, where we get B is equal to h by 8 pi square IC. So substituting B in place of h by 8 pi square IC, we get equation number 1, that is ER is equal to Bj of j plus 1. And the selection rule for Raman spectra is as follows. So the selection for Raman spectra will be delta J is equal to 0, and the next term will be plus or minus 2. When delta J is equal to 0, the Raman spectra radiation will be of the same frequency as that the incident light. That is, the frequency of incident light and the emitted light will be same when delta J is equal to 0. But the transition of delta J is equal to plus 2. Plus 2 will give us a anti-stroke line, that is higher frequency, that is plus gives, that is h nu plus delta E. Since it is a positive sign, we'll get a anti-stroke line that is of higher frequency. Whereas if delta J is equal to minus 2, that will give us a stroke line. Sorry, this is a stroke line. Stroke line, that is h nu minus delta E. Since here we can see a negative line, then it is a stroke line, which actually gives us the lower frequency when compared to the incident radiation. When the transition from J to J dash means, so here J will be the lower state and J dash is the higher state, then change in energy is given by delta ER is equal to EJ dash minus EJ. And since we are considering J as lower state and J dash as higher state, and it is also a common thing that we always subtract a higher number to its lower number, and so thus EJ dash minus EJ is written. And we know for E, here we have got Bj into J of 1. So substituting equation number 1 to this equation, we get delta ER is equal to Bj dash into J dash plus 1 minus Bj into J plus 1, which is equation number 2. The rotational Raman shift will be, so the rotational Raman shift, which is given by delta mu bar is equal to Bj dash into J dash plus 1 minus Bj into J plus 1, which is equation number 3. And here if we consider delta J is equal to plus 2, then delta J is equal to J dash minus J, which is equal to plus 2. Here we are considering delta J. So delta J is nothing but J dash minus J. So here delta J is equal to plus 2. So therefore here also J dash minus J is equal to plus 2. And so thus on rearranging, we'll get this minus J when shifted to here will obviously become plus J, and therefore J dash is equal to J plus 2. Substituting that equation in equation number 3, then we get delta mu bar is equal to B of J plus 2 into J plus 2 plus 1 minus Bj of J plus 1. On rearranging and evaluating, we get B of J plus 2 into J plus 3 minus Bj into J plus 1. So this is in the form of, here we can see multiplication. So we'll do distributive property, that is J into J, J square, J into 3, 3J, 2 into J, 2J, and 2 into 3, it is 6, minus B into multiplying by, we'll take B as common. And so that's J into J, J square plus J into 1 is J. And on further simplification, we'll get B of J square plus 3J plus 2J plus 6 minus J square, minus into plus is minus, so minus J. In both the cases, we are taking B as common, and on further simplification, we'll get B into 4J plus 2. Since 2 is also common, we'll take 2 as a common factor, and thereby we'll get equation number 4 as delta mu bar is equal to 2B into 2J plus 3. This is equation number 4. And similarly, if delta J is equal to minus 2, we had seen the case where delta J was equal to plus 2. Now, if we see it for minus 2, then del J dash minus J is equal to 2. And so on rearranging this, we'll get J dash plus 2 is equal to J. And similarly, substituting this equation, delta nu bar is equal to Bj dash into J dash plus 1 minus B into J dash plus 2 into J dash plus 3. Multiplying them, B into J square plus J dash j square plus j dash minus 5j dash minus 6. On evaluating them, we get b into minus 4j dash minus 6, and therefore we'll get the final equation 5, that is delta mu bar is equal to minus 2b into 2j dash plus 3, which is equation number 5. Now on combination or combining equation number 5 and 6, the Raman shift can be put in the form of, here it is plus 2, here it is minus 2, and the values we have got is also same. So altogether we can give a general equation for Raman shift, that is delta mu bar is equal to plus or minus 2b into 2j plus 3, which is equation number 6. So from here we can see that j can be substituted with the value of 0, 1, 2, 3, etc. And the wave number corresponding to spectral lines will be given in the form of mu bar is equal to mu bar external plus delta mu bar. So mu bar is equal to mu bar external plus delta mu bar, which is given, that is plus 2b into 2j plus 3, which is equation number 7, where mu bar Ex is the wave number of the excited radiation of the Rayleigh line. This is the wave number for excited radiation. Now we'll put different values of j, that is 0, 1, 2, 3, and let us see the value that we get. Mu is equal to mu bar Ex, that is excited radiation, plus or minus 2b into 0 into j plus 3, and so we'll get the value of mu bar as mu bar Ex plus or minus 6b, or plus 6b or minus 6b. This is when j value is equal to 0. And similarly, when the value of j is 1, 2, 3, then the value of mu bar will be mu bar external or excited radiation plus or minus 10b, plus or minus 14b, plus or minus 18b respectively. From equation number 7, that is mu bar is equal to mu bar Ex plus 2b of 2j plus 3, it may be seen that for j is equal to 0, that is mu bar minus mu Ex minus 6b, that is the first Stokes and anti-Stokes line will be at the separation of 6b from the Rayleigh light, that is the value is 6b. So the distance for their first will be 6b. Now further putting j is equal to 0, 1, 2 and etc., the separation between any two adjacent Stokes lines or anti-Stokes line will be 4v. That is when we have put different values of j, that is 1, 2 and 3 and so on, we'll get the value as plus or minus 10b, plus or minus 14b, plus or minus 18b. So the difference between each of the value will be of 4, and therefore the first initial line, their separation will be 6b, and whereas their further it will be plus or minus 4. That is given in case of Stokes lines and anti-Stokes lines, which we have evaluated from our equation number 7. Now let us see the rotational vibrational Raman spectroscopy or Raman spectrum. The selection rule for a molecule to give rotational vibrational Raman spectra is that the polarization of the molecule must change as the molecule vibrates. So as we know, polarization is nothing but the charge which is present upon an atom in a molecule. And so thus when a molecule starts to vibrate, the atoms or the molecule itself should undergo a polarization. So if there is polarization, obviously there will be rise of dipole moment. In case of both type of diatomic molecules, that is for homonuclear or heteronuclear, As the molecule vibrate, the control of the nuclei over the electron will change, and so there is a change in polarizability. That is why both type of diatomic molecule will give a rotational vibrational spectra, which means they are vibrational and Raman active. So to be Raman active, there the main criteria, it should be polarizable, that is change in their polarity. So when any one molecule is under the vibration, the atoms which is present in the molecule, especially the nucleus of the atom, will be participating in the vibration, which actually leads to the vibration. So when vibrations occur, obviously there will be change in the polarizability of that particular atom, which leads to a atom to be vibrationally and rotationally active. When they are vibrationally and rotationally active, they will obviously satisfy the criteria which is needed for Raman spectroscopy, and such molecules Raman active, and so thus we get a Raman spectra. And this is one of the main advantage of Raman spectra over IR, because homonuclear diatomic molecule do not possess a permanent dipole moment. So in IR spectroscopy we have seen there must be a permanent dipole moment, but in case of Raman spectroscopy there will be no need of permanent dipole moment, but we need only the polarizing ability of a atoms which is present in a molecule. If they are able to get polarized, that means they are capable of being active as a vibrational Raman species. The diatomic gas molecule will also give a rotational vibrational Raman spectra, which are generated by a following rule. So delta V, it should be plus or minus 1, and whereas for delta J, it will be 0 or plus or minus 2. So rather than having a permanent dipole moment, to be a Raman active, the molecule should possess only the ability to be polarized, so which is more advantageous when compared to the IR spectroscopy. And however, at room temperature are most of the molecule in their lowest vibrational energy, which we know. At room temperature, almost all the molecules will be in their lowest energy or vibrational energy level, which is V is equal to 0. And therefore the significant vibration transition, which we can expect will be V0 to V1. And restricting to this type of vibrational transitions only, that is from V0 to V1, V1 to V2, and the following result are obtained. When delta J is equal to 0, delta mu bar is equal to omega oscillation into 1 minus 2xc, which actually gives us Q branch. So just know these names, and their detailed explanation we can see in our further sessions when we go deep into the spectroscopic knowledge. And delta J, if it is plus 2, then delta mu bar will give us omega oscillation into 1 minus 2xc, which will lead to a branch called as 2b into 2j plus 3, which is called as S branch. And if delta J is equal to 2, then delta omega bar, which is equal to omega oscillation into 1 minus 2xe, which will actually give 2b into 2j plus 1, which is nearer to it. This is away. Here it is plus 2. So here more amount of energy is given out. So but here less amount of energy is given out. So this comes under S branch, where this again comes under a Q branch. This is actually O branch. And expressing the values for Q, S and O branch by delta omega dash Q, delta mu dash Q, delta mu dash S and delta mu dash O, respectively, and if the wave number of the exciting radiations be mu dash EV, the wave number of the excited radiations of stroke lines is given by, if you are expressing them in terms of EV, that is the EV, or also called as EX, that is the exciting radiations, then obviously the frequencies which are corresponding to the branches, that is Q, S and O, are represented as delta mu bar omega, Q is equal to mu bar EX minus delta mu bar Q, and mu bar S is equal to mu bar EX minus delta mu bar S. Delta O bar is equal to mu bar Ex minus delta mu bar O. And here also we have considered the case for delta V, which is equal to plus or minus 1, which represents the Stokes line, whereas delta V, which is equal to minus 1, represents the anti-Stokes line. That is, plus 1 will represent the Stokes line, whereas minus 1 will represent the anti-Stokes line. They are usually weak, and initially very few molecules that are in the excited vibrational state. Initially, when the molecules are already in the vibrational state, only they can possess such Stokes lines and anti-Stokes lines. And the rotational transitions accompanying the vibrational transition from V0 to V1, and the rotational vibrational Raman spectra is represented. So here also we can see the transition will only be occurred or seen to their adjacent energy, that is plus or minus 1. Hope you all have liked this video and it was very useful for your studies. If you have liked this video, kindly like, share and subscribe. See you all in my next video with a new topic.